You know that feeling, right? That tiny, unexpected jolt of energy that makes you jump? We call it static electricity, but what's really going on under the hood? Let's crack this code. So you're walking across a carpet, you reach for a metal doorknob, and zap! A tiny little spark jumps from your finger. It's this super common experience, but it's also a fascinating little mystery that we are going to solve right now. And really, it's not just doorknobs, is it? It's the crackle your sweater makes when you pull it over your head. It's that little spark when you peel a blanket off in the dark. Or that bigger shock you get from your car door after sliding off the seat. And believe it or not, on a massive, epic scale, it's the exact same science behind a bolt of lightning. Okay, so what is happening in that split second? What is that shocking feeling? Well, our investigation starts right here. Here it is, our very first clue. Whether it's a tiny spark or a huge lightning bolt, the culprit is the same. It's a sudden release, a discharge of electric charges that have been building up. Your body, the car, your sweater, they're basically hoarding a little bit of energy that's just desperate to get out. But what even is this charge? Well, it turns out there's a fundamental two-sided nature to it, a kind of polarity that controls everything. And understanding this is the absolute first key to cracking the case. You know, early scientists figured out pretty quickly that there are only two kinds of electric charge. And you can thank good old Benjamin Franklin for giving them the names we still use today, positive and negative. It's simple, right? You rub a glass rod with a piece of silk, the rod becomes positive, and the silk becomes negative. And this discovery led to the first unbreakable rule of this invisible world. If you take two things that have the same charge, two positives or two negatives, and try to push them together, well, they just won't have it. They push each other apart. Like charges repel. Simple as that. Now, on the flip side, what do you think happens when you bring a positive charge near a negative one? That's right, they pull right toward each other. Opposites attract. And this simple little dance, this push and pull, is the engine that drives pretty much everything in static electricity. So, okay, we've got charges that push and pull, but where do they even come from in the first place? When you shuffle your feet on the carpet, are you, like, magically creating charge out of thin air? Nope, not magic. Turns out we're not creating charge at all. We're just moving it around. See, all stuff is made of atoms, and atoms have positive bits and negative bits, called electrons. All electrification means is shuffling those electrons from one place to another. If an object loses some electrons, it becomes positively charged. If it gains some, it becomes negatively charged. It's all a numbers game. And here's another really crucial piece of the puzzle. Not all materials play this game the same way. In some materials, called conductors, think metals or even our own bodies, those electrons can move around freely, like cars on a superhighway. But in other materials, called insulators, like plastic or wood, the electrons are basically locked in a massive traffic jam. They can't go anywhere. So this leads to a really good question that you can even test for yourself. You run a plastic comb through your hair, and suddenly it can pick up little bits of paper. It's holding a charge. But if you do the exact same thing with a metal spoon, nothing. Why? Well, think about it. The spoon is a conductor. And guess what? So are you. Any extra charge that builds up on that spoon has an escape route. It flows right from the spoon, through your body, and into the earth, which is like a giant, endless reservoir for charge. But that plastic comb, it's an insulator. It traps that charge right on its surface with nowhere to go. So we've got two kinds of charge, and they move through different materials in different ways. But on top of all that, there are these deep, fundamental laws that they always have to obey. No exceptions. First up, charge is conserved. You can't just create it from nothing or make it disappear. It's a zero-sum game. When you rub a balloon on your head, sure, the balloon gets a negative charge, but your hair gets an equal and opposite positive charge. The total amount of charge in the system stays exactly the same. You're just separating it. And second, and this one is a little mind-bending, charge is quantized. That means it isn't some smooth, continuous fluid. It actually comes in tiny, individual packets. The smallest possible unit of charge is called E. It's the charge of one single electron. So any amount of charge you ever find will always be a whole number of E's. You can have 1,000,000 E's of charge, but you can never, ever have 2.5. Okay, we've laid out all the clues, all the rules of the game. But that just leads us to the biggest question of all. Just how powerful is this invisible force of attraction and repulsion, really? Well, let me introduce you to this guy, Charles Augustin de Coulomb. Back in the 1700s, This French physicist built this amazing, super sensitive device and became the first person to actually measure this invisible force between charges. He's the one who finally put a number on it. And here's the absolute essence of what he discovered. The force gets weaker as the charges get farther apart. But it's not just a little weaker. If you double the distance between them, the force drops all the way down to 1/4 of what it was. This inverse square relationship is totally key. So just how strong is this force? Okay, I want you to prepare yourself for this number. The electric force between a single proton and a single electron is about 2.4 times 10 to the 39th power, stronger than the force of gravity between them. That number, that's a 2 with 39 zeros after it. It is so astronomically huge, it's hard to even wrap your head around it. This is not some small, gentle force. It is, without a doubt, one of the most powerful forces in the entire universe.
All right, we have all the clues. We've reached the finish line. Let's put every single piece of this puzzle together and finally solve the mystery of that shocking doorknob, once and for all.
So that little spark you feel, that's not just one thing. It is a massive, sudden flood of countless individual electrons, each one carrying that tiny, fundamental, quantized packet of charge. And those electrons are flowing through you because you're a conductor, all of it being driven by a force that is unimaginably, incomprehensibly stronger than gravity. That little zap is a personal encounter with one of nature's most fundamental and powerful forces. And that leaves us with one last huge question. If this electric force is so unbelievably powerful, why don't we feel it all the time? Why does gravity, which is pathetically weak in comparison, seem to run the show? Well, it's because most of the time, the world is in perfect balance, with equal amounts of positive and negative charge canceling each other out. But you know what? That's a story for another time.